So I think we still have only maybe 50% of students joining. Okay, we're still waiting for another 50%. So we will begin maybe in 3 minutes, I think. Okay.
Professor? Well, my audio must not be working, or you're muted, I think.
Oh, sorry. Yeah, I muted. Yeah, please go ahead.
Oh, sorry, my audio is not working. 1 second.
What? So sorry, I was disrupted by some noise. Yeah. What did you say?
I'm sorry, my stuff just came back on. The question I had was, when I go to the Canvas and I click on lecture, like if I click on files, I can get the stuff. But if I click on lecture, it tells me it's I don't have permissions, access denied.
Oh, okay. So I think you know everything should be in the files. Files will have the lecture. When we collect lecture, do you have access to this? I think this tab is I should actually remove it because it's redirect somehow. You don't really need it actually. Okay.
Okay.
Yeah, I think I can remove this lecture one. I think it's not really needed. Just cause confusion sometimes. To remove it. Yeah, I will figure it out. Oh, this is the earlier code. Sorry, I think it should be this. Lecture. Oh, this is to the previous year, so I think we can just remove it. So let me. Yeah, I need to figure out how to do that. But right now, I don't know. But you just look at syllabus. Okay, in syllabus we will release this 2020. Just let me go to. Yeah, so the lecture tab should be removed. I will try to remove it. Okay, so you can just look at the files. Okay, and or you can just look at the syllabus. I think the syllabus is on. Sorry, I think this is wrong. Yeah, so just look at the syllabus. Okay, we release, let's say, the slides for today here. Okay, and we also have files which actually saves these files. Okay. So the lecture one should be removed. Okay, let me try again. Yeah, it's actually it should not be. Okay. Okay, I think pretty much most students are here. Let's begin. So today we will basically go through this slide. Okay, I already released it on Canvas. Okay, and we also have some hands-on stuff for you guys to try out. Okay, But so we will not market just for you guys to play with it, right? So actually we have another programming project that will be marked, but which is actually, we are talking about some big data security and privacy project, right? So we have a topic 2, which I decided to swap the order because we are still working on the topic 1, right, which is the capture project. I don't want to overlap these things, okay? So we will teach topic 2 next time. Okay, so here we are talking about privacy. Okay, this is the topic for today: privacy preserving data publishing. Okay, for example, if you want to publish some data for research, right, for data mining, for statistical analysis, sometimes this data could be associated with patients in the hospital, right, and or maybe some finance information about investors, etc. Okay, and so this data, if you just release it as is, right, so they can be utilized by other people for different kind of purpose, right? So for your analysis purpose, it's fine, but maybe there's some other undesired purpose that can be utilized. Okay, so in that case, we see that those data may break privacy because maybe your name is there and for example, if it's hospital data, right, your specific disease will be released there, right? Then if you are finding a job, maybe the employer will see, hey, that person is healthier, I want to hire that person instead, right? So that's unfair in some sense, right? So you don't want someone to release the data for like a study, but somehow release your privacy. Okay, so that's a topic we are studying. So how do we publishing data but still protect people's privacy, right? So this is the topic today. So big data privacy is very important because big data is collected from everyone these days, right? You think about your smartphone, your browser, all the browsing trace, right? All the app usage trace, those apps, browsers can collect all your data. Okay, think about Facebook, right? So they have all the data, all the history you have. Okay, on the one hand, they are serving you. Let me see why we have sure active speak video. Let me try to get rid of this. What is this? Let me try to see. Okay. Yeah, I think it's gone. Okay. So on the one hand, you want those companies to know your habits, right? So they can serve you better, right? So guess your next video to watch, like on YouTube, and give you recommendations. On the other hand, you don't want them to utilize the data against you, right? Giving you some more advertisement, right? You don't have so much money, but they keep recommending you some product you don't need, but you seems that you will buy. Okay, so you do want to protect your privacy, right? And so again, after the privacy protected, which means you remove some of your trace on the data, right? The purpose of the data is utilized by, for example, by companies, right, or by researchers, right? So if they get the data, like do a survey, okay, we also need to anonymize the data in some way, right? So you don't want to disclose other people's information, okay? So how can entities use such sensitive data, right? Can we remove the privacy content there, right? But still can mine something useful for the whole population, right? So this is the purpose. So of course we want to anonymize it, right? Because it's privacy. We want to utilize that data, but we don't want you to be able to relate that data to a specific individual, right? Because once you know that individual has some sensitive information, then you can utilize it, okay? But how can we do that? So there's actually a trade-off between privacy and utility, right? So, for privacy notion, you want to do something like a privacy guarantee, right? You don't disclose certain information or totally, or you don't disclose, like people cannot guess that you have that as equally as a random people having that disease, for example, right? So you need to have some notion of guarantee of privacy, right? Okay. And of course, if you don't disclose anything, you're guaranteed 100%, right? So, but that will, the data is useless, okay? So, because there's no data in that. So we need to design a mechanism that still the data is useful, right? High utility, but your privacy is protected. with respect to certain requests, restrictions, okay? So here's a purpose. Basically, if you don't release any useful data, right, so your privacy is totally protected, but the data is not useful for recommendation to help you, right, to make it software easier for you to use or give you recommendations. But, also researchers cannot utilize the data, right, because you want to protect everything, right, your address, right, if you are doing a transportation project, your preferred mode of transportation, right, but if you protect all of these things, then they cannot use the data, basically, okay? So we need to compromise some privacy to make sure the data is useful for people to use, right? But we don't want to compromise to the degree that someone can attack us, okay? So this is what we want to do, okay? We want to release the data, still hoping it can be useful, but we protect individual privacy. So here's an event that motivates the privacy-preserving data publishing, okay? And so this is a group insurance commission, right? So a organization in Massachusetts, right? And so basically they have the health insurance information, okay? So they collected patient data for many employees, okay, in the state of Massachusetts, okay? And they gave this data to researchers or sold to the industry for them to analyze the data, okay? And they actually release the data for people to use, right? So to do data mining for them, okay? But because these are the patient data, the medical record can be related to individuals. If that happens, then the person that gets his sensitive health condition disclosed will not be happy, right? So actually, this happens. The medical record of the former state governor is identified. Okay. So this, you can see this person called Sweeney. I think this is the inventor of a concept called K-anonymity. Okay, so she is we can search for it. I think she did that research in MIT when she pursued his doctoral degree, right? And then I think she, now in Harvard University. Okay, so in professor of practice and government and technology. Okay, so and but early on they have this seminal paper called K-anonymity that we will briefly describe the concept. Okay, we are not going into too much details on the algorithm. Okay, so this Sweeney, she actually originally when was a MIT graduate student, right? At that time, she was not established yet. Right? She wanted to find, for example, some research area to delve into, and she works on like privacy, right, and data privacy. Okay, then she actually played with that data released by Group Insurance Commission. Okay, and then those medical insurance record, she analyzed that. Okay, but when this organization released those records, right, those like a relational table record, the column that contains the patient names are totally removed. Okay, but the problem is that they leave the birth date. Hello, any questions? Okay, let's go on. Okay, so they leave the other three columns, right? So the birth date, okay, and the home zip locations, zip codes, okay, and the gender there, right? Apparently, I think home zip code is really sensitive, right? Because you think about, in the zip code area, and someone births in that particular date, there are not too many people there, right? And additionally, combined with gender, you can recognize who that person is if you are in the neighborhood, you know everyone. Okay, right. So basically, Sweeney, by cross-referencing with another table, right, records from the public voter register, so public voter registration. Okay, then they can, because there is everyone when they register for the voting, right? So they also put their birth date, home zip code, and gender there, right? All this information there, and it's with their name. And the GIC group, right? The GIC organization also released another insurance record table, which contains these three columns, okay? And the health condition, which is sensitive, okay? By doing that, actually, when you do a join, if you know what is a database join, right, on these two tables, right? So you can actually, some of the people are uniquely identified by these three attributes, okay? So this is what's happening. Actually, the governor, you know, record is identified, okay, including his the governor's health condition, okay. And so when you also calculate, you know, about 87% of all Americans can be uniquely identified just using the release table, okay. So that's quite an issue. So here's an example, right? So the GIC organization, and they have a database, and you know, when you do have the medical insurance, you register with them, right? And for reimbursement, or you know, for covering the expense. Okay, so they have all the records in the database, right? And all these patients are collected, information are collected. Okay, and so you will have a table like this. Okay, right? So you maybe the database is looking like this, right? So you have Bob, and what's the date of birth, and the gender, zip code, and the disease. Maybe you don't want the people to know you have some sensitive disease. Okay, maybe this will cause some issue when you're finding jobs, etc. Okay, and so when the GIC released a table for analysis, they remove the first column name. Apparently, we need to remove it. If we have the name there, you basically know Bob has cancer. Right? But unfortunately, there's another table, right? Voting registry. Okay, where so each person who want to vote actually, fill in maybe some form of name and all these information, right? But there, they don't disclose they have cancer. Okay, and on the other hand, so the GIC, right, release this table. Okay, and then by uniquely drawing on these three attributes. Okay, right. So you can identify, for example, for Bob, there's only one Bob, right? So there's only one person that is born in this area and living in this zip code area. Okay, right. And then we know, hey, cancer must be Bob. Okay, Bob must be cancer. Right? So this is what's happening. So this is called re-identification. Okay, so anonymize the name itself is not enough. Okay, apparently you need to remove some other, like a zip code can be removed, right? And the birth date may not be so detailed, right? So actually we can make it less detailed. Okay, maybe we raise the state, okay, or the county instead of the zip code. Okay. So this is one example where if you release the data that involves sensitive information, a sensitive attribute like disease, without care, it can cause privacy leak. Okay, and here's another example, right? So the Aol Data Release. Okay, so Aol released some keyword search results from many users over 3 months period. Okay, and so user IDs are removed, just like names, okay? They're replaced with random numbers, okay? And they actually release the data in the public, for public access, okay? You can just download it freely. But 3 days later, they find, hey, there's some problem, right? So the data will leak some private information, okay? They pull the data from public access, but that's too late because, when you release something into the internet, basically you cannot prevent many people from downloading and save a copy and mirror your data. Okay, so actually, what happens is that even though AOL deleted the search data on August 7th of that year, okay, 2006, but it has been mirrored and distributed by many people. Okay, right, and actually, there's people just want to try to see whether there are some personal information leak, right? And, even New York Times say they are able to locate an individual, right, by cross-referencing with another table, okay, the phone book listings, right, which is publicly available, right? So what happens is this, right? So there's a old lady, right, and who lives in, I think, Lebanon, Georgia, right? So this lady has 3 dogs and frequently search her friend's medical alien, right? So, if you search for your friend's health condition frequently, maybe your friend will not be happy, right? So, so you can see from this search record, you can see there's like a dog and a man, and based on this information, right, these search records, okay, which you can abstract out something like the columns, right? If you want to move them into a table. Okay, then you can search. You can find, hey, this guy is really this lady, right? And because she searched for a dog, right? So she has a dog, right? Has 3 dogs, okay? And frequently search for somebody else, okay? Right? So because the same person also search for other people, like the last name and which county, right? Apparently also disclose her location, okay? And also like a 60 single man, right? So maybe search for friends information, okay? So this re-identification occurred and by New York Times, right? So and maybe it's in the news, right? So the lady must not be happy, okay? So here, why these things can happen, right? So this is because we have so-called quasi-identifier, right? So identifier, we all know what identifier is, right? Because if you learn the relational database, you know that there is a primary key, right? So the identifier, okay? But you can remove that identifier, like the ID, okay? And or you have a unique ID, like your Blazor ID or your name, okay? But even after removing the unique identifier, maybe your birth date and your gender, right, or your address or your zip code is also there, right? If that happens, then based on these several columns, right, I can uniquely identify, hey, that's only you. You are the only possible person. It's impossible for the other person to have the same attributes for these 3 fields, okay? So these 3 attributes that we mentioned earlier, for example, constitute a quasi-identifier, or we say QI, okay? So here, as we summarize here, removing the unique identifiers is not sufficient, okay? The maximal set of attributes that could help identify individuals is called a quasi-identifier. So like the gender, the zip code, and also the birth date, okay? And so QI, is assumed to be publicly available, right? So for example, you can take another table, right? Or you can just Google a little bit, you can find the person information, maybe from LinkedIn, from Facebook, right? A lot of the social network, you will need to fill in your gender, your date of birth, etc. Okay, so they can easily get them. Okay, and then they can find, hey, there's no other people with the same date of birth and the same location, the same region. Okay, then they can identify that's you. Right? Okay, so QI are those attributes that are publicly available, and combined, they can identify you. Right? And then if somebody release some data still contain these columns, then there will be privacy breach. So yeah, and Sweeney and Samarati proposed initially find this problem, right? And then propose K-anonymity, this concept. Okay. What does K-anonymity mean? Right, so each released record should be indistinguishable from at least K-1 others on QI attributes. Keep attention that we are only worrying about the QI attributes. We are not worrying about the sensitive attributes. So that actually also has some weakness, and we will talk about later. Okay. So here we are saying, hey, these 3 attributes combined can uniquely identify a person. That's not good, right? What if, let's say, there are 100 people with those 3 attributes? Then you are not worried that much, okay? Right. So because you cannot say, hey, this must be you, right? Because there are 99 other people there, right? With the same attribute. Okay. And so this K, for example, 100, right, is a parameter K, determining the degree of privacy protection you want. Okay, the larger the K, the more protection you have. Right? Okay.
How do we determine K?
Oh, K is a user-defined parameter. So basically, what you do is you determine the K that you want, and then the algorithm will process the data to satisfy this requirement, which means no matter which 3 attributes you see or which 2 attributes you see, so there will be at least K-1 others having the same attribute values.
So the bigger the K, the more private it is, kind of?
Yeah, so it's a more protection you have, right? So because if you are one of the 1,000 people or 100 people, right? It's better than if you are one of the 3 people, right? Okay. Right. If we can identify 3 people with the same attribute, but they all have cancer, for example, then that I can still, So the more you have, the less distinguishable you are from a bunch of populations. Right? In the extreme case, if everyone has the same attributes, this K becomes the whole data rows in the table. Okay, if you have n rows and K equal to n, this is the most protection. Okay, you cannot differentiate anyone from the table. Right? But if K is 1, then it breaks the privacy. Right? Apparently, and so at least we want a K equal to 2. Right? So 1 others. Right? At least there's someone else. You can say, hey, it may not be me. It could also be him. Right? Okay. But the larger the K is, the more protection you have. But this is only on QI attributes, right? And so that's, but the algorithm will also look at all combinations of attributes, make sure the whole table is privacy protected, okay, not just the 3, because we may have 10 and there are so many different combinations, right? And so, but by the way, so the algorithms are very sophisticated, and we will not describe the algorithm themselves. We'll mainly describe the concept in this lecture. Okay, so if you have interest, you can look into those algorithms. But being aware of there's something here, and there's already some tool and algorithm you can use, right, to protect the data, is the purpose of this lecture. Okay, and we have a hands-on project for your child, and they already implement all those stuff. And so the cardinality of any query result on release data should be at least K, right? So for example, you write a SQL query, right? SQL, right? And then you have some where A equal to something, B equal to something, C equal to something. For any SQL query, okay? The result has at least the K rows, right? So this is basically what it means, right? And so how do you, so right now we have the requirement, right? The release table, we can identify some attributes that belongs to you, there must be also K-1 others that has the same attribute values, right? But apparently our previous table did not satisfy that requirement, okay? So how do we revise the table so that the K anonymity requirement is satisfied? This is the question we're studying, right? So there are 2 ways to guarantee that. The first is called the generalization, right? So what it means is that you want to replace a value with a less specific, but semantically consistent one, right? For example, if you have a zip code area called 35233, right, which is a UAB area, but you don't want to disclose that you are a student at UAB, right? What you can do is you say, hey, this is in Jefferson County, right? It's still consistent, which means you cannot say you are in Shelby County, right? You have to be consistent. It's still correct, but I don't disclose more specific information, okay? It's more general information. Right, so this is replacing a specific value with a correct but more general values. Okay. You can also recode it. Right? So what is by recode? Right? So for example, you have a zip code, right? 35233. Right? You can say 3523 star. Right? It's the last digit you don't disclose. Okay. Then that also protects information. Right? So it's called recoding. Okay. And the other way is suppress. Okay, suppression, which means, hey, I just don't release that attribute value at all. Right? I put a dash there. I say, hey, I don't want to release that. Okay, it's not available. So here's an example of how you can do, so generalization and suppression. Okay, so we are just looking at the zip code, right? Zip code field. Okay, so what you can do is, for example, instead of I say, oh, my 5-digit zip code, which is too specific, right? I don't like it. What I would do is I will just hide, the last digit. Right? So there could be 2 different zip codes having the same digit. Actually, that can be 10, right? 0 to 9. But here's an example. Right? I can go to more specific, but if that is not enough, right? So you can still, even with that, there are only 2 people, right, with this zip code, right? But we have maybe 10 anonymity, right? So then we can go more general, right? We hide 2 digits, okay? And this may be only related to the state level, okay? Another way, I don't disclose any digits. This is suppression, okay? This is this is more like the, what's called the generalization, okay? More general. But here we suppress, we don't disclose anything, okay? So this ground domain are the specific values in the table, okay? Very detailed. Right? And this is just for zip code. Right? For different domain, you need a different, different hierarchies. Right? This you need to provide into the algorithm. Okay, this is like a hierarchical structure of the categories, the values. Right? For example, So here you can say, hey, I want to do a wildcard on the digits from the right-hand side towards the left-hand side. Right? Another maybe the categorical one. Let's say the county, you want to go to the state level, right? So etc. Okay, and the country level. Right? So you need to have a hierarchical structure defined as an input for that attribute. And so here's an example where we require so-called 3 anonymous requirement, right? 3 anonymity. Okay. For the same table, right? So we see this kind of, so this is called a sensitive attribute. Like you have some disease you don't want other people to know, right? Like prostate cancer, right? So this kind of thing is sensitive. You don't want other people to know. And then, but if you just release these 3 data, okay, then everyone will know. For example, if you just know that in this neighborhood, right, you only have one person that is 27, okay? And then you know that that person, maybe Tom, okay, has this disease, right? So then that's not good for Tom, okay? So what we can do is we can hide this information, right? Here we can suppress, we don't give the gender at all, right? Okay, here we are, by the way, as I said, okay, anonymity only works on the QID, quasi-click, quasi-identifier, okay? We're not working on the sensitive attribute, right? Frankly speaking, even you hide the male, right? You can still from the disease, you can guess it's a male, it's the person not a female, okay? Right? Impossible for female to have this, right? But here we are just caring about the QID, okay, quasi-identifier. And so if that is the case, even if you hide it, right? So these 2 are still enough to actually even this 1 column is uniquely identifying each person, right? If you only have 6 people in the table. So what you need to do is you kind of suppress, you generalize and hide the last 2 digits here. But here for this one, if you also hide 2 digits, it will be not necessary, right? Because if you just hide 1 digit, it's already enough, 3 people with the same attribute, okay? Additionally, if you look at the age, right? So these age are all very young. These are middle age, right? So you can give the range for this. For this 20 something, you can give a star, right? So it's like a 28 to 29, right? Something. Okay. So what's the story we get here, right? So the story we get here is that, for example, we can generalize more, right? For example, instead of 1 star, we can make 2 stars, right? Additionally, we can make this range larger, right? Like 40 to 60, right? But that's not necessary, okay? That's not necessary because as long as we can generalize right enough for any people not to be differentiable with 2 others, right? Because it's 3 anonymity, then that's enough, right? For example, now if I see this record released for data mining, okay? I see, hey, there's 3 people with this attribute, right? Even though for example, I want to know that lady, right, with heart disease, right? But I cannot differentiate from the other 2 male, right? So men with flu, for them, okay? So I cannot just give the conclusion that, hey, this lady has heart disease. Maybe this lady this is the lady that has flu, okay? So that kind of protects the privacy. Okay, any questions? Yeah, if you have any questions, just let me know. Okay.
Is the 3 anonymous the same as saying K is 4?
No, 3 anonymous, K is 3. K is the K anonymous. Okay, so basically if you go back to our definition earlier, let me see. Yeah, so you are not distinguishable from K minus 1 others. Is okay?
Gotcha.
Yeah, so you are, so 3 anonymity means you are not differentiated from the other 2. So that's the definition. But it's, you can define it freely, right? So you can say K means cannot differentiate from K, right? So it's equivalent in some sense that you know that 2 definitions, their K means different, okay? But the practice is that K means, there are K, the result is K rows for any attribute, okay? Attribute combinations. So again, you can see that this is not a simple task, right? Because you can have many tables and there's different ways of generalize. Why I want to group these 3, not these 3 together, right? So this is basically an NP hard problem, okay? So it's not an easy problem, and that's why a lot of research are proposed here. And NP hard are I'm not sure how many of you know this. This basically is saying this problem is computationally not feasible. Okay, this is exponential. Right. So, for example, if you have, 2 to the power of something, you think about it, right? And maybe you have 1 million rows. So then 2 to the power of 1 million. Right? So if you want the exact result, the best result. So here we need to define metric, right? So the metric basically says, right, satisfying your requirement of k anonymity, right? So how can we minimize the suppression, right? So the generalization. Okay. For example, if we can hide just 1 digit, we don't hide 2 digits because that is overdoing, and that will hurt the utility. You have less information for mining. Okay. So these are what these algorithms are doing. And here are some names of the algorithms. If you have interest, you can look at them. And they have to be heuristics, right? Because the problem itself is NP-hard. If you solve it exactly, it will run for us maybe 1 million years. Okay, but when you have heuristic, maybe it can finish in maybe 5 minutes or something, and then you can release the table. Okay, and usually, if you also want a so-called approximate algorithm, right, which means maybe your best algorithm here, okay, but in order to find the best one, it will take 1 million years. But you just find a little bit loose than that. Okay, maybe 0.90% of the utility, the cost of suppression or generalization. Okay, well, you can achieve that in 5 minutes. Okay, so these are algorithms are doing this. Okay, and they are still not easy to read. So if you have interest, you can challenge yourself a little bit. So is k anonymity perfect? The answer is actually no. Right. So here's the example. Okay. For example, you know that from some resources, you know that Bob, maybe the phone book, right, is living in this zip code area and has an age 27. Okay, and then you see some institute release some data saying, hey, this table is K3 anonymous, right? Which means for any, let's say, given this row, okay, we can find 2 others with the same attribute. But that's not enough, right? The reason is very simple. If you think about it, all 3 people, because when we talk about k anonymity, we just look at these 2 attributes, right? These are falsely identified, right? We don't look at the sensitive attribute. We don't want to release, right? But now it's possible that all 3 people, right, have heart disease. Right? Now I don't care about which one is you. Right? I know that Bob has heart disease. Okay, so that's a weakness of k anonymity. Of course, if you increase k, right, increase k to 1,000, 100, and 1,000 people, 100 people have heart disease is very low. Right? So k anonymity is good in certain aspect, but for small case, you need some additional protection. Okay, on the sensitive attribute. So this comes the idea of so-called Aol diversity, right? So, Aol diversity, just like a k anonymity, right? So we define a block. Okay, this is one block. This was another block. Okay, so we have Q star block to be the set of tuples, such that its non-sensitive values can generalize to Q star. Okay, like these 2 blocks we see before. Then how can we say that a Q block is Aol diverse? Right. This is only possible if we say that it contains at least Aol different values, well-represented values, okay, for the sensitive attribute. Coming back to here, you see, we only have 1 sensitive attribute, right? So this is not good, because if we want a 2 diversity, at least you have a flu or something else here, okay? Otherwise, we don't think the Q block satisfies this requirement. Okay? So we say that a table is Aol diverse if every Q block is Aol diverse, which means, hey, this is this 2 diverse, right? If we fix this some heart disease to some other like flu, then it's Aol diverse, 2 diverse, okay? Here, this is also 2 diverse, right? This is also 2 diverse, right? In that case, because this has 2 different values, it has 3 different values. Okay, then we say the whole table is 2 diverse. Okay, and that provides a stronger protection over the sensitive attribute. And here you can see that we don't even need k anonymity in the k, right? Because I just need there's enough different kind of disease here, right? I don't care about how many there are here. As long as they belong into the same group, and I require 10 different disease, then there must be at least 10 rows in this Q block. Okay, but as long as you cannot differentiate, for example, whether I have heart disease or flu or cancer or some other disease, right? Then that's fine, okay? Then because you can only guess I have, let's say we have 10 different diseases in a Q block, so you can only guess like 10% of probability you have that disease, okay? So that's another definition that is dedicated to sensitive attributes. But the Q block is defined on non-sensitive attributes, right? So on the quasi identifier, okay? Any questions so far? Again, we are just talking about the definition of the problem, right? So there are very sophisticated algorithms, and we are not describing these algorithms, okay? Just learning the concept, right? So question is error diversity perfect? Right, so still you can attack it, okay? So if you have some background knowledge, right? So if you know that, for example, Yumeko, right? So Yumeko, the Japanese person, okay? And have this zip code area and this age, and you can identify them in this Q block, which there are 3 possible values, right? 2 are cancer, 1 is heart disease. So you know that like 2/3 the person has cancer, but 1/3 is heart disease. It's already disclosed some information, right? Because you know, Yumeko is very likely to have cancer, more likely to have cancer than heart disease. Okay, but if you look at, you know that heart attacks occurs at a reduced rate in Japanese patients, right? Right. So then you know that it's unlikely that, because you know he is a Japanese, right? So you know that it's unlikely this role corresponds to Yumeko, right? Then you have more confidence that Yumeko has a cancer, right? So if you know some background, then when you see some additional information, you can change your belief. So the previous one we described for L diversity is just one of the definitions, but we call it the distinct L diversity, right? So here the meaning is that, you know, we have L distinct values, different values in the same Q block, okay? So each equivalent class, which means a Q block, okay? Equivalent class means the non-sensitive attribute are the same, okay? And has at least the L well represented sensitive values, okay? And so but you can still do the probability inference attacks, just like we said, right? So originally, you know that already 2/3 of probability, most of the probability, Yumeko has cancer, right? And now you know that Japanese is less likely to have heart disease. Right? Yumeko most likely maybe 90% has cancer. Okay. So here's the example, right? Let's say in one equivalent class, there are 10 tuples. Okay, in one Q block, there are 10 tuples. And so in the disease area, the sensitive attribute, only one of them is cancer, one of them is heart disease, and the 8 of them are actually flu, right? So this actually satisfies 3 diversity because, you know, we have cancer, we have heart disease, we have flu, right? But, you know, 80% of people are flu, right? So what you will do is you will just, let's say your boss want to say, hey, what's the probability that person has a disease, right? You will say, what disease is that person? Right? You always say flu because you will guess flu with 80% probability, right? Most likely you are correct, okay? So that means still you can do some better guessing, okay? Let's disclose some information, even though we have 3 different values, okay? Ideally, we want to say that the percentage should be 1/3, right? 33%, not 80%. So this leads to another more rigid L diversity definition based on entropy. Okay, so what it means is that you know, each equivalent class have enough different sensitive values, and so the distribution is also very even, which means you cannot have a bias distribution like 80% of people have flu. Okay, the distribution should be even, right? It's not 8 to 1, right? So it should be almost everyone is close to 30% or something like that. So how to control the distribution? There's a metric called entropy, right? So I'm not sure how many of you know about entropy, at least the entropy in computer science, right? So this is actually quite a popular concept, right? So this describes how evenly distributed your data is, okay? So your data distribution is. Yeah, so how many of you know entropy here?
I've got the physics definition.
Oh, I see. Yeah, physics definition is yeah, it's similar, but in computer science, it's a way of see how even the distribution is. Okay, so basically, you know, it's the idea is the same, right? So the entropy increases, which means the system is more chaos, right? So which means you know, the distribution more evenly distributed, right? It's more random. Okay, if it's cleaner, right? Most of them are fluid. It's very clear. It's fluid, right? Then the entropy will be a very low value. Okay, so that the intuition in the physics is correct, but entropy itself, you know, it's used in a lot of places, right? So, for example, in scikit-learn decision tree, right? In the decision tree model, we need to, for example, when we, let me see whether we can find a decision tree example. Let's see. Right, let's look at this decision tree. Okay. Right. So let's say we have some attributes like the income is high or low, or you know, the student or not, right? And there's some age or something. Okay. So what happens is now you want to depend on that. You want to differentiate whether this person yes or no, which means whether it's safe to loan money, right? So for example, okay. Then originally we have many table entries. Okay. Then maybe some of them is no, maybe half go here, half go here, right? And but this is all maybe QI, that's the non-sensitive attribute. This may be the sensitive attribute you want to get, right? Cancel or not. Okay, and then some will drop here. But one question is this, right? Let's say now we have 100 rows. Some say, hey, this is cancer, this is not cancer, cancer, not cancer. Right? Now, next attribute, which attribute I should use to split these rows further to left and right? Okay. We want, ideally, we want to say, hey, this attribute, let's say age, is so clear that if they are very young, maybe cancer are all zeros. Right? If they are beyond a certain age, they are all ones. Right? Then we can say with confidence, if I have a new row, come down, okay, and come to here, then I say, hey, based on these attribute paths, this guy may likely to have cancer. This guy doesn't have cancer. This is the differential model in machine learning. Okay, so but you think about it. Here we have so many attributes. We can use age. We can also use CR. I don't know what is CR. Right? So we can use the income, for example. Right? There are a lot of things we can use attribute. Which attribute can split the most cleaner? Which means the distribution is the most biased. Right? You think about it, like after splitting, if all are one, right? Let's say we have 6 people. Okay, all are one. Then this is what we say the entropy. The entropy is low, almost zero. Okay, right? Because you know everyone is the same. Right? This is the ideal case, right? So we want to find the attribute. But what if here actually we have mixed case, right? 3, 1, 0, 3, 1. Okay, then you cannot say anything, right? Because maybe 3 of them are like yes, 3 of them are no. So that's an idea. I should not use that attribute to split. Okay. So here for decision tree, it itself has a entropy criteria. Internally. Actually, there are different criteria. So entropy is one of them. Let's look at the. So you can see the criteria can be Gini index, which is similar, okay, and entropy, etc. But by default, you know, when you use it in Gini, maybe the task with Gini is better. We can use entropy to do that, deciding how to split at each step. Okay, so here's an example of entropy. So how is entropy defined? You know, decision tree. Let's look at some post toward data science. I hope they let me read it. Okay, so yeah. So entropy defined like this. Okay, something like here. So which means, for example, let's consider our previous example. So we have 5 rows. This row maybe have heart attack. Okay, and this row has what's that? Cancer. Okay, 2 cancers. Okay, and this one has flu. 2 flu. Right. So how do we compute the entropy? Right. So this is basically says we have 3 different values. So C class is 3. HCF. Okay, and each one have a certain percentage of frequency. So for H we have 1 by 5. Okay, for C we have 2 by 5. For F we have 2 by 5. Right, 40%, 40%, 20%. Okay, and we put this value into this formula. Okay, we get its entropy. Okay, so entropy value is always positive, by the way. Right, so let me see. Yeah. So the reason we have a negative sign here is because this probability is less than 1. Log of something less than 1 is negative. So you cancel this negative. Okay. So here, if you write it out, it should be something like negative 1 by 5 log negative 1 by 5, right? Minus the second term, because we have 3 terms. 2 by 5 log 2 by 5, okay? And minus the same term again, because this is for C, this is for F, okay? So this gives you an entropy. So here's so what if we want them to be perfectly evenly distributed, right? So let's assume this is our Q block, and we want to not only have L values, also these L values are perfectly distributed. So what does it mean by the L values are perfectly distributed? Let's say we have L different diseases, right? So this is L, okay? And each one, if it's uniformly distributed, you cannot differentiate one from another. What's the probability PI? What should be the value here? Who can give me the answer? Okay, so this is 1 by L, right? So for example, you have 3 diseases: heart attack, heart disease, and cancer, and the flu, right? And you want them to be evenly distributed. Let's say you have 9 rows in the table. Right? You want each one have 3 values. Okay, you want each one have 3 values. So this is 1 by 3 each, right? So 3 rows are cancer, 3 rows are heart disease, 3 rows are flu. Okay, then this is the most evenly distributed, right? So L is 3. We have 3 different ones. Each one is 3 by 9. Okay, so the PI. Okay, so this is 1 by 3. Right? So 1 by L, right? You have L values and they're uniformly distributed. Each one has probability 1 by L. Okay, and they sum up to 100%. This is okay. All right. So if you have any question, just let me know. All right. Now let's look at this formula again, and we assume every PI is 1 by L. What will be the result? So this is basically saying you have I equal to 1 to L, right? And a minus P, which is 1 by L, okay, times log 1 by L, okay? Log 1 by L, you can write it as L to the power minus 1. They are the same, right? And you know that if you have the log, this thing can go to the front, okay? And they cancel, basically, right? So basically what we have here is we don't have this minus 1, but in the meanwhile, we cancel this minus 1, okay? So we got this. And so this basically is saying that we sum this value L times, okay? Because it's the same value, right? And then this thing cancels. So we get log L, right? So what's the conclusion here? If you assume that you have L values totally evenly distributed, okay? Then your attribute is log L. It's okay? Yeah, I hope this is fine. And so the reason we talk about all these things is to justify why this is log L. So what is the entropy L diversity, right? It means that the entropy of the distribution of the sensitive values, like the disease, in each equivalent is at least a log L, okay? And as we said, entropy, the higher the better, okay? If the lower the better, right? The lower the cleaner, right? But here for privacy, we want the more chaotic the better, right? Because you cannot differentiate; it's less clean, okay? So the larger the entropy is, the more chaotic your system is, right? So so we want to be at least this value, right? So this or larger. By the way, you may ask, hey, I have L values, and I also want them to be totally uniformly distributed, right? This is impossible. But no one tells you you have to have L different values. You can have more than L different values, right? And then that's achievable. Okay, but it's equivalent to if you have L values, but they're equally distributed. This is a degree of evenness of distribution. Okay, if you have more values, you can be a little bit less uniform. Okay, so this is a threshold. But as you can see, this is quite strict, right? So it's like if you exactly have L values, right? Then you need to be totally evenly distributed. So this is too conservative. Okay, and especially for some values that are very common. Maybe most people don't have cancer, right? But they may frequently have flu. Okay, and in that case, if you want to make flu and cancer evenly distributed, basically you want to, so this is a kind of very difficult to achieve, right? Even inachievable in some sense. Okay. So the entropy of the entire table could be very low, which means even if you involve everybody, right, the entropy is not that high. You cannot reach the log L of quantity you want. Okay. So this is actually not a very practical solution. And then we have the recursive CL diversity. Right? So what does this mean? Right? So this can compromise the definition a little bit, right, of the previous entropy L diversity. Right? We ensure that most common values do not appear too often, while less common values are ensured to not appear too infrequently. What does that mean? That means it's fine you have lots of fluids, okay? But you cannot have just let's say one cancer, okay? And then a bunch of, for example, the heart disease, right? You want to have still some cancers, right? And some heart disease, right? So this is our requirement, okay? So this is, then the distribution more even, right? And another requirement is that if you compare with, the size of this and the size of this, right? It's not too much longer. It's not like you can be, this is one solid, right? You want to have a bound, right? So this is 1, this at most 10. Okay, this cannot go beyond 10, right? Even you have flu, but flu not too many, at most 10 times more than the heart disease or the others. Okay, so how can we guarantee these two requirements? Right. So here's a new definition called a CAL diversity, where C is here. Okay. So this is how it is defined. So in any Q-star block, the most frequent value does not appear too frequently. Okay, right. So which means, yeah, okay, if flu you will occupy most of the slots, right? It's fine, but let's say this is the whole slot. Okay, this is the whole, all the table. Okay, all the entries in the table. You can hold so many flu because the population have so many flu. Okay, that's fine, but you cannot push further, right? You cannot push to here. Okay, but if you push to here, then pretty much, I'm sure that this group is more healthier than the background population, right? Because most of them just have flu. Maybe background population has so many heart disease. Now you only in this Q block you only have this. So this discloses the price. Okay? So how do we guarantee that this flu will not push to the majority, too many of the rows? Okay, so here's the definition. So we just think about, so we should have L different values other than flu. Okay, so this is why we count from L afterwards. So these are, so here's what I want to say. So we may have different values, right? Besides flu is a frequent value, okay? And this is the most frequent, okay? But we may also have another disease, right? These days, COVID is also common, right? So in some sense, okay? And there's also other diseases, right? So like headache, okay? So these are common, okay? And we want to have L of them, right? And they are relatively common. And but they are not so common that, for the rest of rare diseases like heart disease and, the cancer, etc. Okay, these are rare ones, L100, R100. Okay? These are not too few, right? So they combine, right? Like these combine, right? Beyond the first L plus 1 to N, okay? All these combine. they are small, I understand, but if you see times these values, okay, it's gonna be larger than R1, okay? Right. So for example, if you consider C is 3, you can see it's 3, those rare diseases, if you have, let's say, 10 of them, right? That restricts your fluid to not go beyond 30, right? So 30 times 10. Okay? If you go beyond 30, you push too much. That's not good. Right? And in the meanwhile, we also want to restrict R2, also we want to restrict R3, not go beyond 30, right? Can we do that by this definition? The answer is yes, right? Because, R1 is the most frequent value. Okay? Ri is the ith most frequent, right? So which means R1 is larger than R2, okay? And larger than R3, okay? So basically, if R1 itself is bounded by C times the real width, okay? The R2, R3, also all other values are also bounded, okay? So that's basically the definition. So saying that your frequent values, they are L frequent values that are not pushing too much over the less frequent, right? So the distribution is still even, but the evenness is controlled by the C, right? So that's the meaning of the CL diversity. Okay. So this is actually recursively defined. Okay, so because you think about let me see how to see. Yeah, so you can see these IDs, right? So you can continue to define this in a recursive manner. Right? So for example, then within each rare disease, we can also apply this. Right? If you remove R1, R2 also satisfy this, R3 also satisfy this. Okay. All right, so that's meaning of recursive CL diversity. So let me see, communism. Okay, let's finish this slide. So in that case, what kind of attacks can be done over the L diversity, right? So is this still dangerous, right? For example, here we have 3 diversity, right? We have 3 different values, okay? Is this safe now? Actually, there's still some problem, right? So because we require them to have different values, but we don't care what values they are, right? And here, for example, Bob, the attribute match in this cupola, okay? Even though they have 3 different diseases, right? But we know that Bob has some stomach-related disease because all these 3 diseases are stomach-related disease. So we know some information about Bob's weak point, right? So another thing that you can see, other people have a high salary, and the salary of Bob is also very low. Right? So because even though Bob is exact salary not given, but this range is very low. Okay? So that means even though you protect this 3 diversity, but they belong to the same category, right? So you still can disclose something. This is totally different if you have these 3, right? So like flu, it's different. Okay? Or pneumonia, right? It's different. Okay? And so that's basically for the first half of the course. Okay, and we will take attendance. After taking attendance, we will take a 10-minute break. Okay, 10 to 15-minute break. Let me go here. Yeah, by the way, if you have any question, please feel free to ask. Okay. By the way, all these definitions are well recognized. So there are existing algorithms that you can just call like packages and just anonymize data. Okay. All right, so let's take attendance. So what I will do is I will sample some students. Okay, I think we also have a graduate student list. Yeah, so a PhD student. Okay. Kamal. Kamal. How about the Kamal? Flying Chaudhary? Are you here?
Hello.
Oh,
Can
okay.
you hear me?
Yeah, I can hear you. Yeah, I'm taking you.
Okay, thank you.
All right, so let's continue. So I will sample some students here. So Jushra, are you here? Jushra?
Yeah.
Okay.
I'm here.
Okay, thank you. And Gahada, are you here?
Yes, I'm here.
Okay. Sai.
I'm here.
Okay, thank you. Anakin, are you here? Annika?
Yeah, I'm here.
Okay. Shauna? Shauna, are you here? Shauna? I see the chat. Just let me open the chat. Oh, by the way, so there's a question asking about KCL values. So this is your definition. Okay, you define some requirement, how much privacy you need to protect. Okay, and then the algorithm will revise the table to the minimal degree to satisfy these requirements. Okay, so if you define it too strict, then the data will be less useful. Right? This is what you define, and the goal of these algorithms satisfy requirements. Shana, are you here? Mahesh, are you here? Oh, Mahesh Bun? No. Chen Yu, are you here? Hello? I think the attendance is surprising a little bit. Okay, so Vivek, are you here?
Yeah, I'm here. Yeah, I'm here.
Okay. Alakia.
Yes, sir. Yes, sir, I'm here.
Okay, thank you. Let me. Varun, are you here? Varun?
Yes, I'm here.
Okay. Philip, are you here?
I'm here.
Okay, thank you. Gaussian.
Yes, Professor, I'm here.
Okay. Achana.
Yes, sir, I'm here.
Aditya, are you here?
Yeah, I'm here.
Okay. Santosh, are you here?
Yes, sir, I'm here.
Sandeep, are you here?
Yes, I'm here.
Say Lee, are you here?
Yes, I'm here.
Okay. Manhu,
Yes, sir, I'm here.
Katha, are you here? Katha? No. Sushmita, are you here? Sushmita? No. Hello?
Hello? Sir, I'm here, Sushmita.
Sushmita, okay. Brandon, are you here? Brandon?
Brendan Turner, that's me. Yep.
Okay. And Hamid, are you here? Hamid? No. Ziming, are you here?
Yeah, I'm here.
Okay, thank you. And Cranty.
Hello, Professor, I'm here.
Okay, thank you. Yeah, I think there are some students not here, and if somehow I missed you, just let me know. Okay, I think. Okay, so that's for now. Let's come back maybe.
Hello, Professor.
Yep. Oh.
My name is Mahesh. I am also there. I think you might have missed my name.
Okay.
Mahesh Bang.
Okay. Right. So yeah, we will come back maybe 6:20, 23, 24. Okay. So I think.
Professor.
Yeah.
I have a very quick question regarding the L diversity. It's defined based on the number of parameters we take, right?
No, L diversity is let me see. L diversity is
No, I mean to say like the L diversity is defined based on the number of different parameters in particular you could say column.
Yeah, I understand what you want to talk. So basically L diversity, the basic definition called L diversity, which means in the Q block, you have all different values in the scientific attribute, okay? But that may cause some problem because the distribution not good. So besides the L parameter, there's also some other differential, like a CL diversity. Right? So then you also introduce a C value here, and there are different variants of L diversity. This also constitutes attribute. Okay?
Okay.
Okay. Yeah.
All right.
You're welcome. Okay, so we will come back in 6, 20, and 25. Okay, so in between them. I think there are some questions. Oh, I think there's no standard, but these are well recognized concepts in academia, right? So, okay, anonymity. But these days, actually, we will talk about differential privacy. Okay, so this is quite a popular concept here, right? So even in NIH, they have some. So these are less used these days. Okay, there's another concept called differential privacy. We will see that in the second part of the lecture. Okay. I see another student asking, Brian. Yeah, I think you are here. Okay.
Thank you.
Okay. Yeah, so okay, let's come back maybe 6:20 or 6:25. I will be here at 6:20, but I will wait for a couple minutes. Let's assume 6:20. Thank you. See you later. Okay, I see a message, so I just handled it. Okay, so we are beginning, but let me see. So maybe we are beginning in 2 minutes. Okay, get prepared. Thank you.
Hey, quick question about the homework. So I noticed the end is the question, like, is it right? And then I did it for a few and mine did not return correctly. So is that kind of what we're getting at, that it's not going to be correct?
Oh, so you mean
the CAPTCHA, yeah.
So there's a small detail there. I'm not sure whether you are aware of that. Let me give you an example. Okay, so just to make sure you did this, right? So for example, each file will have a file name. Okay, right? So for example, you have ABCD, right? And we have the ABCD file name, and we also have those contours of the ABCD capture.
Yep.
And you need to align them, right? So you need to say, hey, this is A, right? This is not A, okay? This is D. So you need a step that sort them by the center of the bounding box, okay? And then you, from left to right, you align to the file name character. Right? If you don't have that step, maybe that will cause issue. Do you have that step?
Yes, to like get them into each folder and make sure that they're in the correct folder. But you're talking about breaking down the actual CAPTCHA image with the model. Okay.
Yeah, exactly. You need to say, hey, this A is label A, right? So this is the image. This is its label A, right? So you need to put all of them into a folder named A.
Okay.
Yeah. All right. Then these folders, you have X, which is the image pixels. You also have Y, which is A, right? Then you can give to our, convolution network, okay? And then if you train them with these correctly split data, it should be able to predict the letters, okay?
Gotcha. I have them in the correct folder. I was just having trouble breaking down the CAPTCHA image, so I need to make sure I'm going left.
So you need to, after you get those bounding boxes, they can be any order, right? You need to start them by the center's X coordinate, right? And then you can match them from left to right, okay?
Gotcha. Sounds good.
Okay, you're welcome. Okay, let's begin. And yeah. So this is what we just covered, right? So let's continue. So here, this is the conclusion. Aol diversity did not consider the semantic meanings of sensitive values, right? Even though these are different values, the semantic meaning are very similar compared with flu, right? They are all stomach-related disease, okay? So in that case, we actually, there's still some problem here, right? But Aol diversity does not protect that. So there's another concept called T-closeness, right? So T-closeness moves one step further on the distribution, right? So we wanted the distribution of the sensitive attribute to be close to the distribution of the overall table for that sensitive attribute, okay? So this is very similar to, the Bayesian theory, right? So, in the whole population, let's say we know that if you go to a hospital, maybe 50% have flus, right? But now, let's say in this cube block, this small block, you find that, for example, 90% have flus. Then you know that it's more likely that a patient who fall into that cube block is having a flu than average person, okay? So then you gain some information. This is called information gain, okay? So before you see that quasi-identify, see any attribute of the person, right? You have a prior belief which corresponds to the entire table, okay? Maybe on those 1,000 patients, maybe 800 have flus, okay? Now you think 80% of that person has flu, right? After you see that table, that you see the attribute, and you correlate them into a cube block, you see that in that cube block, maybe 99% of the patient are having flus, right? Then you are more certain that the patient has flu, not heart disease, okay? So here, T-closeness basically want to close the gap, saying that any cube block, okay, their distribution should be similar to the overall distribution, right? So the idea is quite different from Aol diversity. Aol diversity says you should be as uniformly distributed as possible, right? So you should not have bias. T-closeness says you can have bias, that's fine, right? So, but your bias should be the same as the entire population, right? you cannot zoom in and then find, hey, this distribution quite different, okay? And so here's a definition of the T-closeness, right? In any equivalent class, the distance between the distribution in this class means the cubic level, okay? And the distribution of the entire table should be no more than a threshold T, okay? So here we again need a distance metric for two distributions, right? One is the distribution of the disease for the entire population in your table, right? Another is after you zoom into these, let's say these 100 rows that belong to the same, quasi-identifier values, right? So there's another distribution of those disease, right? So these two distributions, one is called P, one is called Q, right? Maybe this is 10% flu, this is 90% flu, right? So in these two distributions, if we measure the distance between the distribution, it should not be too far away. Okay? It should be within T. Okay. So maybe you are not familiar with distance between distributions, right? So basically, there are different metrics. Okay, so you can measure distance between two values for sure. Right? They are absolute value difference, right? And so if you have Euclidean space, two locations, right? You can do a Euclidean distance. Okay. But there are also other distance metrics, right? Like if you have two vectors, you can also use cosine similarity. And if you have two distributions, there are also like a Lewis-Mover distance, like which is used by here. There's also like a cross entropy, right? Cross entropy is another kind of distance. I think we discussed last time for two distributions. And you can also have, for example, between two matrices, how close they are, right? You can use a Frobenius norm of their difference matrix, okay? And L1 distance, L2 distance, LP distance, right? So there are different distance metrics, okay, which are very important actually in data analytics and machine learning. Different algorithms use different metrics. Entropy is another metrics, right? But that's univariate, right? So which means you just give one input, okay, one operand. It's operator on one operand, right? Here it's a distance metric on two operand, okay? Right, so here in this work, where they first proposed the concept of T-closeness, they use two kind of different distances. One is called a variational distance, right? Which means, hey, if you have 10% flu, but that guy has 20% flu, what's the difference? Absolute value. Okay, this difference, but you do this over all the categories. So this is a pretty straightforward definition, right? So there's another definition called Earth mover distance. So which is well-defined, but actually a lot more complicated, okay? So how to understand the concept, right? So this means you have some earth, right? So the mud, I mean, for example, right? So what to use them? Let's say you have a hill, right? So you are saying that, hey, this is one distribution, right? This is one hill, okay? I want to move to another hill, right? To the other district. This is P, this is Q, okay? How do we do this? Maybe I will take these mud to here, right? And these are too many. We'll move these to the left-hand side. And how much you move until you kind of satisfy this become the same. This is called Earth mover distance, right? So this is like how much flow you go from this particular I to this particular J, right? Or this should be negative, right? Because you want to, this should be positive. You moved from here to here, okay? Because you have the values and they are probabilities, right? So they are fractional probabilities. So you want to move so that their shape becomes the same. So this is a flow, how much you move from the i's value to the j's value, okay? Right, and this d is the weight, how important that weight is, right? So let me see, how far away they are, no, okay? For example, this I and the j, if they are adjacent, that's fine, right? But if you move it longer, right? So you carry this earth longer to here, right? So that will cost more. This is the distance between these two values, okay? And this is the magnitude, how the amount of mud, right? So you take from one place to the other, right? So apparently they should satisfy some requirements. This is the optimization point. One, minimize the amount of work you do to change one shape to the other, right? And of course, the amount you move from I to J should be the same, right? From the heart disease to flu, okay? And now, so after moving, digging out these, but moving these from J to I, but also add I to J, right? The amount should be equal to the destination distribution, okay? And their total amount should be 1. This is distribution sum to be, okay? So you solve this optimization problem. This gives you, the distance, right? This will give you the values. right? And then you put it there, you get the minimum distance. Okay. So this is just a concept. It may be a little bit complicated, but you know that the Earth movers distance is what defined. It's a metric between two, matrics. Okay, for distribution. That's basically. Intuition is just the Earth mover. Okay. Right. So here's the result of the closeness. Right. So you anonymize data with 9 rows. Okay. And finally you get some result like this. This table, if you compute the Earth mover metric, right, the T, because we want the distance from the background table, and each group should not be too much different. Okay, so you can see that regarding salary, this T is small, and regarding the disease, this T is a little bit larger, right? So salary, you can see, so this distribution, you have something in the low end, you have something in the high end, right? Each group has something in the low end and something high end. So their distribution is quite similar to the entire table, right? You have 3, 4, 6, which is relatively low, and you have 9, 8, 10, 11, right? So the distribution, after you gather information, you zoom in this group, right? And this distribution is not too far away from the entire distribution. Okay. Any questions? So for different attributes, you will have different T. Okay. So again, this T is a user-defined structure, right? T closeness protects against the attribute disclosure, but not identity disclosure. So you can still, based on these values, right? So you still know someone, right? So it is within these 3, okay? But the distribution of the sensitive attribute is even. Right? For example, maybe in this Q block, ideally, we want a K anonymity where K is equal to 100. Right? But here, actually, we just have 3. That's not so safe. Right? Only two different people cannot differentiate from, okay, based on the attribute. But actually, the salary is already very evenly distributed, and I mean, very close to the background distribution. So, but it doesn't protect your anonymity. Okay. All right. Any questions about T closeness? If not, we will go on. Okay. So far we are talking about the relational tables, right? So what about the graph data? Graph means nodes and edges. Okay. So for example, if you think about a social network, right, a Facebook, right, and these are the Facebook accounts, different people, right? And if you are mutual friends with another person, then you have a match. And then based on that, for example, Facebook company can construct a graph like this. And then they want to release this data for other people to use, right? So for recommendation of products, right? This is quite common. For example, if you purchase some product, maybe your friends are also likely to purchase something, and Facebook want to make that money, right? If that's the case, if Facebook will show the same advertisement, right? So wrong. Okay. Let's say so. This graph data is useful for graph mining. For example, if you look at Dan, right? If Bob, Tim, Ann, and Ever all by iPhone 12, so then likely I should recommend the iPhone 12 also to Dan, okay, instead of some other phones, right? Okay. But if we directly release the data, but we hide the names, right? Instead of Bob, I say 3. I give different IDs. Is that enough? That's not enough, right? Because if you look at this graph, and again, you know that Dan has 4 friends, right? Then you can differentiate Dan, right? Dan has 4 friends, right? Tim, Bob, Ever, and Joe, right? And in the meanwhile, you know that Tim and Bob, 2 of them are friends themselves. These 2, Ever and Joe are from different communities, right? Like this is like maybe elementary school student, classmate. This may be the college classmates. These are maybe high school classmates, right? So they may not know each other, but these 2 may know each other. Okay, if that's the case, right? And you somehow know this, right? And then you can uniquely identify 6 is Dan. Okay, why? Because no other vertex satisfies this. For example, 7 only have 2 neighbors, right? Only Dan has 4 neighbors. Okay, and the 2 of them are the same. Okay, so then even though you replace with 6, based on some background information you know, you can still recognize, hey, this is Dan, right? So basically, this structure, only 6 has this structure, okay? So Dan is re-identified. So how do we hide the identity, right, of the graph node? Okay, And even link, sometimes we want to hide. Maybe it's two people communicating, but you don't want to know that. These two people don't want the other people to know. So identity disclosure and link disclosure are the problems, right? So how do we avoid those things, right? So there are two ways. One is we can modify the agent vertex link, random permit. For example, I can change this attribute. Right? I can randomly connect some of them. Right? For example, I can connect because 5 only have 3 friends, right? And 1 and 2 are no. I change a little bit the graph, make 5 also a friend of 9. Right? So for example, so we make a small change as possible, right? So this data is still useful. Maybe some inaccuracy noise introduced, but still useful. But if we do this, then 1, 2 are friends of each other, and the 5 has 4 friends. Okay, 8. Okay. Then you never know whether it's 5 or 6 if you release this graph. Dan could be 5, Dan could be 6. Okay. In that way, you protect Dan's identity. This is like 2 anonymity. Right? And so, how do you do some modification? Agent vertex to certify, for example, k-anonymize, right? But you want to do as small modification as possible, right? If you change totally the graph, then that's useless, right? So what you mine is not what actually meaningful. Right? If let's say you have 100 friends, I change 2 or 3 friend links, right? It's still accurate if you recommend an iPhone, right? And maybe 50% of that friend, 50 friends of yours by iPhone. Right? But somehow I swapped 2 friends, right? But there's still 48, okay? Right? So it's still accurate. But if we don't want to totally change the subgraph. Okay? Small change so far. Okay. So this is one method. The second method is to group vertices and edges into partitions called super vertex and super edges. Right? So this is called a node contraction. For example, I can contract these 3 nodes into 1 node. Okay. And then basically, 2 is connect 1, but I say this super node is connect 1, right? So you never know is 2 connect 1 or 6 connect 1, right? So this is called a graph contraction. If you do something like this, then again you protect privacy because no one understands who. So these 3 are anonymized, right? You never know who is who. Okay. So this method is similar to generalization, right? So if they are in a nearby region in the graph, we will generalize it to 1 region.
So we replace the 3 nodes with 1 node, basically?
Yeah. So this is kind of one solution. So there are different solutions, but we can. This is called a super vertex, right? So there's a concept called graph contraction. You can take it. Again, all those are very sophisticated algorithms. Okay, and graph 1 is even more complicated. And so because this is not an algorithm course, so we are not paying too much attention. But I think we can look at an example of what is a graph contraction. Let me see whether we have a vertex contraction. Maybe I don't see a better example, but let's just look at this. For example, we have U and V, right? And this edge, I want to not differentiate to U and V, but I just make it W. Now U is connected to, for example, this node, this node, this node, this node, right? And V is connected to this node again, this node, this node, this node. Now after contraction, W is connected to all these. Okay. Then you never know whether because you only see W, you don't see U or V. Right? You know that maybe this guy is in that group, but I never know whether it's U that is interacting with this guy or V interaction. So that protects it. The privacy of it. It's okay?
Yes, thank you.
Yeah, it's just a high-level concept. Okay, the details are very sophisticated, and if you have interest, you can delve into. So these are the tools that you have accessed. So this concept is very similar to the generalization. Generalization suppression, we don't have that suppression unless we delete that edge. But the super vertex, super edge is like the generalization. Right? Generalize these 3 into a more specific, more high level supernode. Right. So next, let's move to another concept called differential privacy, right? So differential privacy is a very popular term. I'm not sure whether you've heard of that. And it's actually in a lot of products these days. Okay. And so this is probably more practical than the other, the other stuff. Okay, so like here, Anonymity. This is more popularly used these days. Okay, so this is actually defining based on another kind of concept, right? So the risk to my privacy should not substantially increase as a result of my participating at statistical, right? So what does it mean? You want to hide the information whether you are in a group or not, right? So whether you are joined, let's say you are joined this class or not. Right? I don't want people to know whether you choose foundational data science or not, right? So, and we want to make sure that the statistics doesn't change a lot, whether you join the class or you didn't join the class. Right? So, for example, this is understandable, right? For example, the counting is one popular, popular example of differential privacy, right? But another example that is very difficult to hide, right? Because if you count, but you add a noise that is more than one, right? For example, you have 100 students, but then you will randomly add 5, 95 to 105, right? Then it's very different to know whether you are in the group or not, because you add some small noise. A difficult example for differential privacy, for example, if you take a max, right? For example, if you a bunch of students are here, but suddenly Bill Gates joined the group, right? And the max of the savings, for example, will just increase significantly, right? So then it's very difficult to add noise. Right? You need to add a noise that is ridiculous, so that that you immediately know whether some super rich guy is here or not. Okay. So yeah, so this is basically the concept. Without or with you in the database, your privacy risk should not change much, right? Only in that case, I can report that metric, like a count, okay? If the max salary, maybe we should hide it, right? So because it's not safe, okay? And a lot of the applications are popular because they are just doing counting, right? So like how many clicks, right? How many people view that page, etc. I give a number that doesn't disclose who visits the page, okay? So that's the concept. So let's look at a strict definition of differential privacy. Right? So basically, as we said, maybe you have a count, right? There are 1,000 people visit the page, but I don't want people to know whether I visit the page or not, right? So how do you do that? Right? You can add a small noise. Okay, you can add a small noise, no matter whether you have background or not, right? Maybe you know that 999 people already visit the page. If I visit, it's at 1,000. It should be you, right? And then that's not safe. What I can do is I add maybe a noise of 5 randomly. So 0 to 10, right? Some random noise sampled from there, okay? And add to the count. So now I get a number, let's say 1,003. Right? That number will not disclose whether you are in it or not, because the sampling process is already random, right? You are in there, you are not in there, the probability will not change that much, okay? So this is the concept. So we want to add a noise. So we want to randomize the function k. That gives, so this is a privacy parameter, epsilon. Okay, just like a k, anonymity, Aol, diversity, there's a parameter, epsilon differential privacy. Okay, this is called the privacy budget. So if for all data sets D and D prime differ on at most one row, right? So we are protecting everyone's, every individual's, every row's privacy, not just yours, right? Maybe you have 100 people, everyone should be safe. Okay, so if any row, if you remove it or you add it, right, becomes D or D prime, right? So the probability that D belong to S, and then the probability D prime belong to S, right, does not change much. Right? For example, if you D is after removing you from D, you get D prime, right? Then you are in D or you are not in D, the probability that the count is 1,000 is almost the same, right? Still 90%, right? And this probability is generated by the distribution, the noise distribution, right? Gaussian over 5. Actually, we will see we are not using Gaussian, we are using Laplacian distribution. Okay, that's for some reason to satisfy this definition. Okay. So how do we limit the difference between these two databases, right? The probability of the two databases. So we are using epsilon, but we use exponential epsilon. Okay. So how can we understand this exponential epsilon? Let's get intuition on the next page. Okay. So usually the epsilon should be a very small value. Okay, it's a small value. So if that is the case, we can show that exponential to epsilon very close to 1 plus epsilon. Okay, exponential minus epsilon is very close to 1 minus epsilon. This only holds if your epsilon is very close to 0. Okay, and if we use this formula, you can see that it makes sense to you, right? You know that they are not too much different, right? For example, epsilon is 10%, right? Then that means whether you are in D or you're not in D, okay? Then it's not much difference, right? So the probability that the count is 1,000 visits, right, is changing by a very small fraction, okay, only 10%, right? Maybe you are in D, so probably 90%. You're not in D, 80%, right? Then that's fine. Okay, it's not like if like a Bill Gates is not in the group, then suddenly the max salary drops, right? Okay. So how can we add a noise, right? So we should add a noise using particular distribution, right? And we need to prove that this distribution can satisfy this formula, right? So do we have? By the way, so we keep in mind that this definition is very strict. It's for all data, any two pairs differing among them. Okay, if you find one pair of data that does not satisfy this requirement, it's not a differential privacy. Okay, so for any two databases that are different by 1 row, okay, this should always satisfy. And so let me see. Yeah, another requirement is that for that metric, for all the ranks, okay, for all the, no matter how large the class size is, if the class has 10 students, the class has 100 students, this range, okay, this should always be satisfied. Okay. All right, so we actually, there's a very simple and nice proof show that this can be satisfied using Laplace distribution. And what is Laplace distribution? It's very close to Gaussian distribution. Okay, but Gaussian distribution, you cannot prove that property. Okay? Using Laplace distribution, you don't have square here, right? It's very close to the epsilons. Okay, then you can satisfy the requirement. But here, this B is just like the width of the distribution, right? So like in Gaussian, what's the standard deviation? Okay. So this B controls is relevant to the epsilon we want. Okay. So let's visualize what is the Laplace distribution. This is very close to Gaussian distribution, but this is a tip. Right? This is not a smooth cap. Okay, this is a tip. So this is the Laplace distribution, right? And when you add noise, you want to add a small noise, right? So like if you are 100 people in this class, then maybe you add a small noise, most likely within 2, -2 to 2. I don't want to add a very big noise. Okay, so ideally we want that. But if your epsilon is very small, then you probably have to use the blue one to satisfy that. Okay. There's a relationship between epsilon and B that we will see later. Okay, so basically we will, based on epsilon, we'll compute B, and based on the B, we will sample a noise, right? So from here. Most likely within this range, okay? Most likely 2 or 1, something like that. And sometimes very small probability with sample 6, okay? And then you add to the data. Because of probability, right? So the randomized probability, then you have something to play with, like the definition. Okay. Here, let's look at the next page. So here's the concept, right? Let's say this is the exact value. This is the original value. So 100, okay? But you know that you will add a random noise on it. The random noise may be maybe -2, right? And -6, something like this. This will change your actual turnout value to be a distribution, okay? Like this black line. And if you, for example, you pull out a row or you add a new row into your database, this distribution will change to here, right? But it's fine, right? Because according to that rule, if you add for this epsilon, if you give that b and you use that plus noise, you can guarantee that if you look at any value here, remember we need to guarantee this for any value in this axis. Okay. Then if you compute the ratio between two probabilities, right? Then the one ratio is this one, okay? And another one is the orange line, okay, this one. Okay. The ratio, the difference is within that exponential to the epsilon bar, okay? So this should hold for every line, okay? For this line, okay? This ratio still holds. So for example, if you compute the height of this, let me see. You compute the height of this, and you also compute the height of this. These two bars, they are still within epsilon. Okay, so any location along this axis, right? We have that guarantee. And the nice thing about it is that you can prove if you add Laplace distribution, you can prove that you will always satisfy this, okay, which is approximately this. Again, why? So if you are interested, you can look at the proof. It's not difficult, but we are skipping. So here's a theorem. So the mechanism of adding noise, right, is like this. Okay? So Laplace have a parameter b. The b should be computed as delta f divided by epsilon. Epsilon is what you give, the requirement, privacy degree you want for that. The smaller the better. Okay, but there's also a concept of delta f. Okay, so what is delta f? Delta f is called the sensitivity of your problem, your function. Okay, an example is, for example, let me see whether we have that definition. So maybe we can go to Wikipedia. That will. So yeah, this is called a sensitivity. What does this mean? This means because you want to report if, maybe the count of a data, right? So a database, right? And so D1 and D2 are differential by one row, okay? And the sensitivity is saying, hey, for any D1, D2, right? So for any two Ds, okay, any pair of D1, D2 that are different by one row, okay? If you give this statistic you want to report, they're different. What's the max possible value, right? And for count, why count is a popular data we want to report? Because for count, it's always one, okay? Right, because if your size is different by one, f is a size, and then this is always one, okay? For no matter D1, D2 is one. But for some other statistics, maybe that would be different. For example, max, it's a lot more complicated, right? So put simply, if you just want to count, it's very simple. It's if you want epsilon, like a 10% differential privacy, like this 1 by 10, okay, 1 by 0.1 is 10 would be equal to 2. Just add that noise, you are secure, at least to the 10% differential privacy, right? So here in the example where we have the true answer is 100, right? But you may add a one row to 101, or you may go to 99. Okay, and here if you give the noise, right? So you cannot differentiate because the ratio between two bars in any values are like within that bar. For example, if you see 102, then you know that without you 102 is maybe 45%. Okay, with you the percentage is 40, maybe 41%, right? So within 1%, which is within that exponential to the exponent. Okay. Any questions so far? Yeah, so you can see that this concept itself is a little bit complicated to describe, right? So this is privacy research, okay, but this is the first step, right? So if you know the concept, you can use these tools, right? But if you want to do research there, then you need a lot of mathematics, algorithms. Because how do we achieve this? We have not described it here. And so next we have a theorem, which is very nice, okay? So this theorem basically says, if you have k queries, right? You want a k candidates, k1, k2, k, m1 to mk, right? And we know that each operation, like count, etc., right? Each operation is epsilon I differential private. Okay, then the combination of them is actually summation of epsilon differential private. Okay, so this property has to be proved. Okay, so why this is nice? Because if this is like money, right? If you spend $1 on this query, spend $2 on the second query, spend $3 on the third query, then 1 plus 1 plus 2 plus 3, you spend $6 on the second query. Okay, you are still secure to epsilon 6, right? And if you have a budget, let's say you have $10, then you can split them in different queries. Right? Maybe that query count I need more accuracy. I can put a larger budget, maybe 5 to count. Maybe for other statistics, right? So I give a smaller budget. Okay? So this is additive. So this is a very important property of differential privacy. So far we talked about differential privacy. So how do we do that, right? So if you want to count how many users visit your page, right? So what you do is everyone just send your data, right? Like say in our example, we just send 1 because I visit you, right? And then it will take the sum and add a noise. Okay. So this is assuming that, for example, when you are using Chrome, right, and the Chrome is collecting your visits to pages. Okay. You are relying on Google, okay, to be trusted, right? And the Google, if it does not add that noise and just share with somebody else, right? Then you're in trouble. Okay. Maybe somebody know that so far there are so many, like 4 people. Only these 4 people will be visiting that page, and the other will not. But I'm not sure about you. Then you send 1, then that's fine. Then I know, hey, you also visit that page. Okay, so that's not nice. But if I add a small noise, you cannot differentiate. But who knows whether Chrome will report that or not, right? So we'll add noise. So we don't want to rely on a third party to add noise for us. Okay? So what we can do is we can add a noise by ourselves and then send it out. Right. So if we do this, right, to the database, and then these data will be aggregated along with the noise, right? And then people do the data mining. This is called a local differential privacy, right? So the benefit of the local LDP, right, is that you don't need to worry about trust with server. Okay, so these are the concepts. This is a relatively late, recent concept, not so recent. I would say maybe 5 to 10 years. Okay, the other concepts are really early. Right? So like anonymity, probably last century. Okay, yeah, but again, I want to emphasize this. Right, so some of them are really designed for a restricted class of problems. Okay, for example, for counts and those things built on counts, like histograms, maybe even for some data mining algorithms that rely on frequencies. Right? A lot of them rely on frequencies. Then you can make sure these operations are differential privacy. Epsilon differential privacy. Okay? But for a lot of others, maybe you cannot do that, like math. Okay. All right. So finally, let's look at some application of DP, differential privacy. Right. So this thing is actually already widely deployed. For example, in Chrome, right? So it's used to collect the browsing statistics, right? Because Google want to know, say, 1 million people visit that YouTube page, right? But you don't want to Google to tell others, hey, you visited what page, okay? Right, so maybe Google will flip a coin and say, hey, this guy 80% visited, 20% of it, 0.8 instead of 1, okay? Right, and that protects you a little bit if you use local difference. Right? So Google will just get the exact number, right? Maybe 200 people visit, then I add a small noise, 5, and save it in the database. Okay, and then I report to the people when they do search, how many visits. Right? And another example is iOS, right? And, Apple, right? So they also collect your typing statistics, right? So this is like what words you type, right? So and what's the frequency, etc. Okay, and Microsoft also collects some telemetry data time. Okay, and Snap also perform like user preference by collecting some data from you. Okay, but they do the differential privacy stuff so that it does not disclose too much of your information. Okay, all these applications actually have over 100 million users each. So this is actually already functioning in the real world. Okay. And so we have a assignment, right? So there's a Python library called DP, Differential Privacy Statistics, from the Rutgers University, right? And they have some differential private operations already, like take the mean value, take the variance, histogram. So principal, PCA, support by machine, logistic regression. These things can all mine data, but protect your differential privacy. Okay. I think this is let me see, what is this? Somehow this link is no longer there. So, but I think, yeah, because I searched for it, it's no longer there. But I think you can just Google. Let me see. If you just Google, let's say, this packet name, okay, DP statistics, I think you can find it. So this library, I think previously, I don't know whether it's in GitLab or GitHub. Okay, so you can do some differentially private operations. Right? So for data mining. Okay, again, when you have a large epsilon, it will be not so safe. Okay, so this differential private machine learning statistics library. Okay, I think this they are supported and the National Science Foundation. So they are sharing these things. Okay. And we have assignments that we will not mark. Just if you are interested, you can try it out. Okay, we will release after this class. Okay. So that's basically the end of this slide. Any questions? Okay. If not, then we will continue. Okay. So we will go with the next program assignment. Hands-on project. So if you remember, this is topic 2, right? So we will not release a programming project, this week. Okay, we will release it next week, which is yeah. Let me mute. Yeah. So because you have an ongoing programming project, right? So we want to know overlap, right? So we will release this next week, and we will not finish it this week for sure, right? Because there are a lot of slides. Okay, and we will. I think this slide is not put in the syllabus. I will also add this. Okay, so after this class, I will put this slide on the syllabus. You can directly download on the dynamic syllabus. You can also play with the differential privacy package. Okay, we have some Jupyter notebook to you for you as examples. Okay, so let's continue. So previously we studied that we say some deep learning model is so powerful that some technology is totally abandoned or outdated, right? So for example, the capture, okay? And this is something that is reversed, right? So with the development of deep learning, right? So again, so we are using deep learning previously to attack capture, right? But can we attack deep learning itself? Is deep learning so good, so robust? The answer is actually no. Okay, so we are looking at this aspect here, right? So CM is convolution net we discussed in the first class, okay? Oh, in the second maybe, okay? And so we say that these convolution nets can also be attacked. Okay, so this is the topic of this slide. And so here's example that the data science technique is not robust to security attacks, right? So so what we are saying is basically if you have an image classifier, you think it's a cat, but we change 1 pixel, for example, you will think it's a dog, right? I mean, you will not think it's a dog, but the machine learning model, the deep learning model will think it's a dog, okay? And so again, we are studying deep learning, but this time we are not using deep learning to attack something else. We are directly attacking deep learning model itself. So attack technique is called a data perturbation. Right? So we basically we are working on images. Basically for the image, we add some small noise, right? And actually the classifier will totally misclassify this image. Okay. So this is associated with the assignment, right? So we'll have a project to attack a convolution, right? So originally we'll have a trend model. It can differentiate, let's say, cat, dog, and a car, but then you will write an attack model, change the image a little bit where you as a human can still recognize it's a cat. but the machine learning model was totally mispredicted, like a dog or a cow. Okay, so this is what we are looking at. So this kind of research is called adversarial attacks. Okay, adversarial attacks on deep learning models. And again, so this is not restricted to images, right? So you can also do it on NLP, natural languages, and a lot of other things like videos, right? So, but here we are just using images as an illustration because this is the simplest example. Okay. So deep learning models are actually vulnerable to adversarial attacks in the form of a small, subtle perturbation to the input, right? And that will lead to a model to predict the problem into a totally wrong class. For example, if you look at this image, right, this is a car, sports car, okay, to predict a sports car. But if you can compute a noise, a small noise, right, like this. It may look very noisy, but actually, scaled up so that you can see the noise. It's actually very small in terms of pixel values. Okay, and then you add to it, you will get this image, right? As human, we can still recognize it's a car, but it's maybe a low quality, right? This is a very clear car. This is a little bit not so clear. Maybe you think it's a lower resolution, but it's actually because we add some peculiar noise here. Okay, but after you add this noise, the prediction will be wrong. It will think it's a toaster, right? It's totally wrong, right? Because it's a car, it's not a toaster, right? So how do we compute this noise to fool this deep learning model to do a wrong prediction? That's a problem. Okay? So here's a recap of what we see so earlier, right? So we know that the deep learning model starting from AlexNet, right? So it suddenly improves a lot, right? From 25 error rate to 16 error rate, and then all the way to like, the ResNet, okay? And this is even better than human prediction, right? But we are just working on those COMNETs, okay? We want to fool the COMNET, right? So here's a example. For example, we have different models, right? This is CafeNet, as we mentioned. CafeNet is just an AlexNet, okay? AlexNet, originally when they train it, they need 2 GPUs because the GPU memory is too small, right? And CafeNet is just say, hey, not GPU large enough. I just use 1 GPU. So the architecture is the same, okay? So you can see the original image, you can, you know this images class, right? This is a particular kind of tree. But if you add some noise, you can see there's some noise up there, right? But you can still see this is that tree, right? But actually your class will be totally wrong. Okay, and the confidence of the wrong class is very high, actually, right? Almost 90%. Okay. Now similarly, you have a bird, right? A jay, right? But if you add a little bit of noise, it will predict as wrong as a mask. Okay, and the probability is very high, 80%. Right? So I think 80% is the mask, right? Which means the probability that J is less than 20%. Okay. And here's another example, right? You have a pepper. Okay, so if you add some noise to the pepper, right? Compute small noise. As a human, we can still see it's a pepper, right? But somehow, the model will think it's a strainer, right? So it's totally wrong. Okay. So these are attacks. And why this problem is important, right? So maybe for the images, it's just for play, right? For you to play. Right? It's not a serious problem anyway. Okay. But if you think about the track sign detection, right? Whether it's a stop sign or not, right? So where the stop sign, etc. Right? And detection means not only what it is, also where it is. And so that's require a lot more complicated models. I think if you take my machine learning course, you have tried a detection model earlier, right? So because our final project on that. Okay. This time we will try a segmentation model. Okay. We'll talk about it later. And so here, if you want to recognize whether there's a track sign, stop sign or not, right? This is the binary constraint problem. Right? And if let's say you change a little bit of the pixel, then you think, hey, there's no sign. Okay, then we are in trouble because if it's a self-driving car, right, you should stop. But because of some signal, like this reflection of the light, suddenly some pixel is changed and the stop sign is not detected. What can happen is that you will not stop and then you will crash with another car. Okay, so that's possible. So that will have some real world issues. Okay. Another thing is that you can do actually what's more surprising actually is that you can when we take a picture of 3D objects, right? like the turtle, right? So we can always assume it's the model will detect the turtle, right? But very interesting, you can print some turtle, 3D turtle, right? But you change some of the pixels, the colors on the turtle, okay? And then you print it, and then take a picture and let the model detect. It will detect it as something else. Like here, the red class is turtle, right? The green class is correct. There's no correct predictions here, okay? And most of them, they are classified as a rifle somehow, okay? Right? Maybe because of the color, it's a little bit red, right? So, okay? And there's also sometimes it detects other classes, but never as a turtle, okay? Even if you print it out and change some of the color, things will go wrong, okay? So that means, for example, if your stop sign has some pixels flipped, things can go wrong, right? So we need to study this problem, right? Attack is one problem. There's also another problem for defense, okay? So let me change this. Yeah, so I think previously we make the final project open project. Now we don't have it, okay? Because we want to not to reuse the same project for different data science courses. So we'll focus on convolution net classification problem, okay? But attacks can also be used for object detection, and also can be used for generative models, right? And it can also be used for recurrent neural, etc. Okay, so this is a general concept, adversarial attack, basically. Okay, and you have attacks and you have defense, right? If you have attack and I want to add something so that my classifier is more robust, right? I'm less likely to detect a turtle as a rifle. Okay, so that's an independent topic, right? So there's also a lot of research there. If you have interest, you can study. All right, so what are the different kind of attacks? Right, so there are some key concepts we need to understand. Right, the first one dimension is whether it's a black box attack or it's a white box attack. Right, so that means if you have a white box attack, you know exactly I'm attacking that model. Right, so like a Google Net. Okay, so I can design attacking method specifically to that model because I know its design. Okay, black box attack means that I don't know the model. Right, how it's designed or what's the details of the model. I cannot utilize the model to help me generate a noise. Okay? Basically, I want to attack, but I don't care about what convolution net it is. I add this pixel, I should fool most of the convolution net. Okay, so this is black box attack. The second concept is whether it's a one-step method for adding noise, right? Or it's a iterative method, right? So this is usually for the white box attack, right? So you can add some pixel and then see, hey, whether the model is performing poorly. If it's not poor, then I choose the next pixel, and which is more effective for the model. Okay, so you can do iteration after iteration. But there are also methods that just change one particular pixel, and it will totally predict things wrong. Okay, we'll see that later. And another is concept important is target attack or not target attack. What does that mean? Okay. So here, for example, we have three classes. Okay, so we have an image. And we have three classes: cat, dog, and maybe cow. Okay, three classes. Right. So the concept of target attack means whatever you give me, right? You give me a photo of dog. Okay, I want to predict as a cow, right? Because I have a target which is a cow, right? Non-target attack means, hey, you give me a dog image, right? I can as long as I fool you, that's enough. As long as you don't predict as a dog, I'm done. I don't need to move to the car. You can also say this is a cat. Okay, so this is non-target attack. Target attack means I have a target class in mind. I want you to just predict everything to that class. Okay. Another concept is transferability, right? Which means, hey, if I fool this model, okay, and then people may use, we have so many convolution nets, right, in that challenge. Okay, so can I? This image I changed, can I also fool that model? Right, so this whether it's transferable. Okay, obviously if you are too white box, you are dedicated to like the Google net, maybe you cannot fool the ResNet. Okay, right. So maybe more general black box attacks performs better. Okay, and finally, there's a concept of adversarial training. Right? So what is adversarial training? Adversarial training means now that I can generate so many misclassified samples, right? I can get as a feedback to the model. and then train the model again. Say, hey, you are predicting this wrong. You should tune your model parameters a little bit and to make it correct. Right? So this is adversarial training. We can add some wrong prediction back and help the model to predict correctly. Okay. So one particular example is so-called, I'm not sure whether you heard of the GAN model. Okay. Yeah, generative adversarial training network. I think we should look at the image. So, yeah, what it does is actually, you wanna have a real image in the classifier, right? So real and fake. But you also want to have, you generate fake images. These are generated images, not real images. Okay, and you also fill these fake images, right? So this is a kind of adversarial training. Right? Okay, so then this actually sometimes it's for the purpose of generator. You want to create a generator that can generate images that are just like real. Discriminant cannot differentiate real or fake. Okay, but sometimes you want to train the discriminant to be better because real image is not enough. I want to fill some more data, but I want to train this generator to generate images just like real images. Okay, then you can train the data. There's other variants. For example, you can have InfoGAN. So for example, it's different GAN model. Besides the real fake, I also want to predict whether it's scattered dot. Okay, so you can have different models. Yeah, so that's the concepts. So firstly, let's look at one particular algorithm. Right? So this algorithm is called the fast gradient sign method. Okay, this is a one-step method, which means that you just have a parameter epsilon. You want to add a noise, right? So what you do is this. Okay, so this is called a gradient ascent. Okay, what does it mean? So you have let me go to a deep learning model. That may make sense clearly. Okay? Because we will do the project, so we need to make the concept crystal clear. Then you can understand it better. Yeah, let's look at this image. That's good enough. Okay. So who can tell me when you train this model, what are you training in this model? When you give a model image and you give the class, right? So what are actually you are training in this model? Okay, so the answer is they are training those weight matrices, right? Like this filter, where we will do inner product by sliding the window. Okay, we'll train each of the weight matrices. Here, this is basically a big fully connected layer. This is the big weight matrix, right? So these are the what we are training. Okay. So when we take a derivative, we are taking derivative of these parameters, so we can do gradient descent, change these parameters. Okay. What is not changing is, for example, the input. The input is the fixed image, right? Although you can take gradient to the input x, right? But that doesn't make too much sense because the input is not changing, right? We are tuning the weight matrices so that your input and y, x and y, they match, y hat and y close, right? So this is the original machine learning model for training the convolution net. So in the attacking model, we are adopting a totally different solution, okay? So the attacking model, we assume the model is already trained. So these things will be fixed. You will not change them, okay? You can still take derivative to them, like these weight matrices, but you will not change them. What you are changing is the input image. This input image will change it, okay? So now, when you take derivative, actually directly take derivative all the way back to the input image. Okay? You are taking not to take partial derivative, not to W. You will take partial derivative input image, okay? And you compute the noise that we will add to it. Okay, so that's a derivative of the noise we want to compute. Okay, so this is one thing that you need to know. The second thing you need to know is that when we are training the regular convolution net, right? We are doing this. Okay, we have a y, which is the ground truth class, but the model will give you a y hat, right, which is a predictor class. Okay, and from them, how far away they are, we will compute a loss function. And that's what our target function will take derivative with, right? And we want to minimize the loss. Okay, we are doing gradient descent. right? So which means if your gradient is some value like g, and you will take a small step in negative gradient, because gradient is where your value increase, the loss increases fastest. Negative is decrease the loss, decrease the error, okay? But you go start small step, and next time you compute again, next time again, until you reach the lowest error, okay? So this is the gradient set. This is negating the gradient, okay, for the weights. But here, if we think about attacking models, right? Now these weights are fixed, right? So this image is what we take the gradient with, right? But what's our goal? So now instead of the gradient of w, right, we have a w, we want to take gradient over x, okay? Epsilon. But our goal is not to reduce error, right? Because when we reduce error, you will predict it as a right class, okay? We want to increase the error, okay? That means instead of negate, we will use plus, okay? Right, we pull it away from the small loss. We want to make it have an error, which means we want to pull away y from y. Let's say y is cat. I want to pull away the projection to dog, okay? As far away from the cat as possible, right? So this is a high-level concept that you need to be aware. And now let's go to here, right? So that's y, okay? So this is the gradient. This is the Jacobian, right? So this is the gradient over x, and your y is the true class, right? You want to push away from the true class. You take the gradient here, but you will use a plus sign, right? Because you want to increase the loss. So this is called a gradient ascent, okay? The non-gradient descent, right? Because you want to increase this loss function, right? Okay? You want to increase the j is the loss, okay? Take a derivative of j to x, this is notation, okay? So this is your loss function j, right? This is x. Okay? You want to take a derivative from j to x, right? But you want to go to the direction that is increasing, okay? Not decreasing. But you think about it, what if the gradient is super big, right? Then we are in trouble. So we will use sign, right? Sign means if it's positive, the value is 1. Negative is negative. Okay? We want to change it a little bit, but not too much. The degree of changing is using epsilon. So if you change to the right direction, you should increase that pixel, right? You just change a little bit by epsilon, right? If you decrease the pixel, you also cut by epsilon. You will not go beyond epsilon, right? So the direction is right, but the magnitude is controlled, right? So that's the method, and this is shown to be working, right? So basically, we want to push away from the true value. Right? So this is your true. Okay. So this is one method. Apparently, you need to know the model. Right? So unless you know the model, you know the loss, right? Because we know this is the deep learning model. This is the function of this. Take the output to here, all the way, and this is the function is relying on all those. The gradient rely on all the model. So this is the white box attack. Okay, and when you compute the delta x, right? So you just add it. Okay, so this is the gradient step. Right? So you add the gradient to the original image, you get an adversary. Okay, and likely if you put it back, it will give you a wrong prediction because this time loss is big. If loss is big enough, then definitely will be. Okay. So another model is called targeted model. Right? So previously we say it's untargeted. Okay, as long as you move away from y true, whatever wrong class, it doesn't matter to me. Okay. So next is called a targeted model. Right. So that model is slightly different. Okay. So when we take gradient, right, we wanted the loss. Right. So your prediction. Previously we say the prediction, the distance. Let's go to the previous page. Okay. Previously we want your prediction. Right, your y hat prediction by the model and the true class. Oh, sorry, I think I go to the wrong page. Previously, if you give x to the model, it will give you a y prediction, right? This prediction and the true value, right? So there is some difference. I want to increase that difference, increase the loss. Right? So I use plus. Okay. Now in the targeted model, it's different. Right? Here you can see we use a y target. Right? Why? Because if you give the x to the model, it will give you a y hat. Right? Instead of want to pull them away, you want to pull y hat to y. Right? So we want them to be close. Right? So that's why we use minus. We want to minimize the loss function, but we are not giving the ground truth target. Why? Not the y truth. I'm giving the target class output. Okay? And then you are moving towards the target class direction. Okay? The others are the same. Sign, so each step is just epsilon, not too much. Okay? Any questions so far? These are all, white box attacks. Okay. The next one is called the iterative. Again, you may ask, hey, I don't know how to take the derivative. Don't worry about it. TensorFlow handles that for you. Okay. So you know the idea, then you can make it work. As in our next one. Another is called iterative method. Right? So what does that mean? Right? We don't consider target version. We call it a target version, which means we want to move away from the true class. Okay. Right, we will do this step by step. This time I change the pixel a little bit, and next time I change the pixel on different direction because each pixel is changing. This is actually, our input is a whole image, which means each pixel has a direction. This may increase, this may decrease. Okay, so I can do this iteratively, right? So no one tells me I can do it once, right? Maybe once the probability that I make it accurate is very low. Right? Now I can, instead of one step with a budget of epsilon, I can make it t iterations. Each just use one fraction of the budget, which is alpha. I change it iteratively, and hopefully it will go in the right direction. Right? Because one step, maybe your guess is not correct. You go a small step, then you see, hey, I should have come up. Okay, step by step. That will be more effective, right? So this is the iterative fast gradient sign method. So this is better for white box attacks, but not as robust to black box attack because this is too much to the architecture of the model, right? Yeah, I will continue next time, right? So, and we will release a project for this next time also. Today I will release the differential privacy project for you to play with. You don't have to submit it, okay? Just if you have interest, you can play with it. If you don't have interest, you can skip it. These concepts are important, right? The second is, so I will put this slide also on the data show, right? Okay, so that's all for today. And I will be here for 1 more minute. And unless you have no question, I will disconnect. Okay, thank you. I will also upload the video to YouTube and send the link with announcement.
I got another question about the homework.
Okay.
So we are only touching the sections that say to do for our code, and everything else should be left alone, correct?
I think so. But usually inform the guests, okay? But I think we have some locations tell you need to fill this. Most of the code are already there for you. Okay?
Gotcha. I was just confirming.
Yeah. So it's like 90% is written for you. You just complete some of the missing ones, and do go through all the code. You need to go through all the code.
Oh yeah.
To understand the concept. Okay. Yeah. Okay. Any other questions before I disconnect?
Nope. Thanks. See you next week.
See you.
Thank you. Bye.
Bye.
Thank you.
Okay. Thank you.
Thank you.
Thank you.
You're welcome. Okay, so then I will disconnect. If you have any questions, just send me an email. Okay, see you next week.